In fact, I arrived here in '84. The department was less than 20 years old at the time. I wasn't very familiar with universities, so I didn't realize that this was really there's no other department like this one in the world, then somehow I just stumbled upon it. It really was the ideal place for a young guy who was interested in combinatorics to come and learn. The number of courses I could take, the people I could learn from was phenomenal. So, I'm very grateful to this department for looking after me so well, and I was delighted to be asked to take part in the celebration of the special year. I checked your YouTube channel to see what other people are doing in this series. That explains some of your clicks. So a couple of people recommended reading Tut's book on his collected papers. And it's a good recommendation. I'm going to recommend a similar book. Many of you are familiar with this, but perhaps some of you aren't. Here he gives full chapters describing some of his work, where he discusses, how he became interested in it for the first time, the thought process. I was talking to this person who made this remark that made me think that is really great. My favorite chapter is the one on Hamiltonicity. He talks about his counterexample of Tate's conjecture and how he came up with it. And there was three really good ideas. And when you put those three ideas together, that graph just jumps right out. And when I used to teach that lesson in my intro graph theory courses, I'd say, well, here's a conjecture, and I'd draw this elaborate graph on the board, and I'd say, look, it's not Hamiltonian, and that's the lecture, right? But now it's a much better lesson. Now I can say, well, here's how you'd think about coming up with a counterexample, and here's what his thoughts were, and boom, here comes this graph. It's wonderful. In that chapter, he says, there's three good ideas, but it took him several years. He says he had his first idea in 1940, and he says he was surprised looking back how long it took him to finish it off till 1945. But then he simply says, but of course, up to the last month of that year, I had more pressing business. All right, so on to today's talk. The Lovász local lemma. Some of you know it. It's really a bedrock result if you were going to work in the probabilistic method. If this was just purely a probability course, this would be a great thing to feature. It basically says, you got a bunch of events. If they're all independent of each other, then of course there's positive probability that none of them happen. And this says you can actually introduce a little bit of dependency, and still the probability that none of them happen is positive. So that's very interesting from a probability standpoint. But from a combinatoric standpoint, it's very, very useful. The probabilistic method, the idea is we want to prove that something exists. A graph with a certain structure exists. A solution to a problem exists. A coloring of a graph with certain properties exists. And the way we go about doing it, this is something Erdős pioneered many decades ago, is you come up with some random way of constructing that object, that coloring, that graph. And you want to prove that the probability you succeed is positive. And when you're first learning this, you expect someone to say the probability to succeed is very high. But no, it's actually very low. It's exponentially low, but positive. And that's enough, because if the thing didn't exist, then the probability of success would have to be 0. Okay? So this proves that it exists. So when we want to apply the probabilistic method, we need a statement like this: a probability is positive. Okay? And what's this no bad events business? Well, we describe a set of bad events to say all the bad things that might happen, the things that could go wrong. We win if none of the bad things happen. Okay? So we want this. The probability that we win, that we did something good, is positive. So maybe the simplest example is KSAT. Let me just make sure everyone knows what KSAT is. So it's a Boolean formula. Maybe it looks something like this. So we've got a bunch of Boolean clauses. Each one has exactly 3 literals in it, and we want to satisfy and have the whole thing evaluate to true, which of course means, because they're ANDed together, each of these evaluates to true. Okay, so we want to come up with an assignment that satisfies all these clauses simultaneously. Okay. And the local lemma tells me that I look at the Boolean formula, I look at the maximum degree if I view it as a hypergraph, right? So this clause intersects, i.e. shares a variable with at most d other clauses. And as long as d isn't too big, then it's satisfiable no matter how big the whole graph is. Okay. And how do we prove this? Well, I said with the probabilistic method, we look for these things randomly. The simplest thing you would try is just flip an independent coin on each variable to come up with a random satisfying assignment. And my bad event is going to be, well, bad event A1 is that this clause comes up bad, it's unsatisfied. Bad event A2 is that this clause is bad, and so on. And if none of the bad events hold, that's exactly the same as it was a satisfying assignment. And what's the probability that this one is bad? Well, every one of these variables would have had to come up the wrong way for this clause. So 1 over 2 to the k. And so as long as e times 1 over 2 to the k times d is less than 1, we're satisfiable. That's all there is to it. And I think this would be a hard thing to prove without the local lemma. I don't know, I haven't tried, but it certainly is a lot easier with the local lemma. So the local lemma tends to work really well in settings where every variable is given an independent value. Here I flipped a coin for x1 without looking at x2 and x5. Okay? The reason for that is that if two clauses do not share a variable, then in this setting I can treat them as independent. Okay? And so I get the independency I need for the local lemma. Okay? It doesn't work as well. It's much harder when you want to, for example, color graph one vertex at a time. Okay, so most of the time when we do graph coloring with this, we do something like this. Give every vertex an independent random color. Okay? But you'd really want to control things a bit better. You'd want to sometimes maybe say color the vertices one at a time, each time give a vertex a random color that doesn't appear in its neighborhood yet. That makes a lot more sense. But the problem is the dependency spreads through the graph like wildfire. Because, I'm a vertex 100, distance 100 away from the first one. But the color I gave to the first one affected the list of the next one. That affected the list of the next one, and so on. So we get a lot of dependency. Okay? So it's very hard to do. The thrust of this lecture is going to be that we now have a technique, a variation of the local lemma, where we can actually sometimes analyze this type of thing, and that gives us a lot of power. So the story of that starts with an algorithm. So the local lemma gives a existence proof. The satisfying assignment exists, for example. The probability that you get it is very small. It's exponentially small. And so you don't immediately get a nice, simple, even a randomized algorithm to produce it. And so at one point, up until the 90s or so, it was a very big problem for all of us who are working with the probabilistic method, is how do we come up with efficient algorithms to actually find what the local lemma guarantees? And we made some partial progress, but the big breakthrough was by Moser somewhere in the mid-2000s. He gave a very simple algorithm for example, for KSAT, and a similar algorithm for most of the applications. So start with any assignment you want, and look at it. Is it a satisfying assignment? Well, let's say it's not. Then pick some clause that is violated. There's got to be one. Maybe this one's wrong. Then I'll just flip the coins again for those three variables. Okay? And maybe I got unlucky and it's still unsatisfied. But if I do it a few times, that'll become satisfied. But it might mess up another clause. There used to be a satisfied clause containing x5. Maybe it had an x5 bar in it, and now it's messed up. But we just keep doing it over and over again, and we hope for the best, and we hope it terminates. Now, all of us who are working on this knew this algorithm should work, or thought it should work anyway. Because as long as the number of clauses intersecting this one is small, then we wouldn't expect this to mess up very many others. And so this should peter out and terminate eventually. But the analysis of tracing the effect through the whole formula was just too complicated for us. We couldn't do it. But Moser came up with this beautiful, elegant proof that this works. The technique he introduced to do it, I think it was Terry Tao called it entropy compression. Now, entropy can mean some complicated stuff sometimes. This time it doesn't. This is all I mean by entropy compression. This is the only thing you need to know about entropy. You can't represent a random string with a shorter string. Okay? That's all there is to this. Okay? And what do I mean by represent it by a shorter string? Let's suppose I flipped n coins, and I wanted to tell you what they all turned out to be. So the most straightforward way is if I flip 100 coins, I tell you 100 things. Heads, heads, true, tails, heads, and so on. Okay? But maybe I come up with a scheme. My scheme will be something like this. Well, if they're all the same, I'm not going to tell you everything. I'll just say it was all heads. And that would be a short way for me to tell you what happened instead of listing them all. Okay? Or if it's all tails, I'll say that. But if this is my scheme to try to compress my random string, odds are I'm going to fail. Okay? I'd have to be very lucky to pull this off. Okay? And so basically, there's a number of ways to phrase this, but one way is this. If I've got a scheme which will represent a random string of bits by a string that's much shorter, then with very high probability I'm going to fail. And you just count how many possible 100-bit strings could be represented by my 80-bit compression. Not very many. Okay? It's very, very simple. So how does this help here? Well, we're going through this algorithm, and at every step, we're going to flip k coins. So by the end, I've got a long sequence of coin flips. And if this algorithm goes for a long, long time, the algorithm is going to give me a short representation of that sequence of coin flips. Huh? A contradiction. And so that will prove that it cannot, in fact, go for very long. With high probability, it will stop before too many steps. And what's some intuition why this might be true? Well, at every step, we've found a clause that's unsatisfied. And so there's a set of k variables there that were assigned at some previous point randomly. And instead of telling you this one came out false, this one came out true, this one came out false, I could simply say this whole clause is false. And that gives me a compression, a short way of telling you the outcomes of a whole bunch of previous flips. And if I'm careful with that idea, you can really pull it off. You can, by saying something like this a lot of times, I can, in a short way, tell you what all the coin flips were while carrying out the algorithm. Contradiction, so with high probability, I'll fail to go for very long. So I'll modify the algorithm a little bit. I'll call this a history file. We'll keep track of the history. While there's any violated clauses, I randomly reassign the variables in one of them, and I'll name that clause at C, and I'll just simply write down I fixed clause C. Okay. And I carry on for T steps where T is big, and I'm not claiming I've finished. In fact, I more want to say that I don't go on very long, so pretend I've gone on for T steps and really haven't gotten anywhere. It's still unsatisfied. And so I wrote down just a long sequence, fix C7, fix C12. I had to fix C12 twice because it got messed up afterwards, and so on and so on and so on. So I've forgotten my coin flips. I've only kept track of which clause was fixed in each step. And I claim that if I write down that list and I give you the current assignment, the assignment I'm at, you can reconstruct everything that happened. Okay? And why is that? Well, just work backwards. So I've given you a current assignment, and I tell you that the last step was fix this clause. Okay? So I fixed that clause, and then I got the current assignment. Well, you know that before that step, this clause was false. So before that step, x2 was true, x7 was false, x12 was false. So you can take the final assignment, change those three variables, and you get the second last assignment, step t minus 1. Okay? And then I tell you what was the second last clause fixed. So you get the second last assignment, and so on and so on. You work your way back, and you get the every step of the algorithm. And so, indeed, you get all the coin flips. Okay? And that is going to be, that's a way for me to tell you what all the coin flips were. Okay? So the question is it a short way? Did I win? Huh? Oh, it's upside down. Is this a short representation? Okay, is it shorter than k times t bits? Right? So t times I wrote fix this clause. Instead, I could have t times just told you k coin flips. Okay? Well, certainly if t is small, if t is 1, it's not, because I got this extra thing. I got to tell you an entire assignment. That takes n bits. Okay? So picture t being big, so big that this is negligible. Okay? I just want to know, do I win on these steps? Is writing fix C7 shorter than telling you, let's say k is 100, all 100 coin flips? Okay? I mean, it looks shorter, right? I'm cheating a bit here. Does anyone see what I've done? Yeah. Well, I picked these nice small numbers like fix C25. Okay? In reality, we want to picture this happening on maybe an enormous formula where the number of clauses is like 2 to the 2 to the 2 to the k. And for me to give you the number of a clause, I've got to give an enormous, 2 to the, what did I say, 2 to the 2 to the k digit number. So the number of bits it takes me to name that clause could be huge. So I didn't really win. It might take more than the number 25 to name that whole clause. But we haven't used the small degree business yet. And the solution to this is that the small degree gives an efficient way to name the clauses. So, when it's time to do, say, fix C25, the reason I have to fix C25, it might be that C25 was bad from the start. There'll be some clauses that were bad from the start, but that's kind of a one-time only thing. If I go a long way, it's because a lot of clauses got messed up during the process. So in order to fix C25, it's because maybe C12 messed it up. Okay? And so instead of saying fix C25, where 25 might be a very, very long number, I'll say fix the 8th clause intersecting C12. I'll point to the clause that messed me up and fix the 8th one doing it. Okay? And if I can get the pointer in place, how much work does it say fix the 8th? Well, this number 8th is something between 1 and D, because C12 only intersects D clauses. Okay? So D being small gives me a nice small neighbor, nice small label. Let's pretend it's really simple and I'm always being messed up by the guy immediately before me. Then this becomes very simple. Okay? Of course, it's not always immediately. There might be there's some sort of tree-like structure going on, right? To embed the tree-like structure, it only costs you an extra order 1 bits per step. It turns out it's not very hard. Okay? So that's what we do. The number of random bits that we actually flipped is t times k for each step. The size of the record is, well, that plus n for the final assignment, and basically log d is how long it takes to write the number 8. Plus an order 1 for some business to take care of the tree structure, which is actually quite simple. And so that multiplied by t plus some one-time only bits. So as long as this is less than this, log d plus order 1 is less than k, i.e. as long as d is less than some constant times 2 to the k, then I win. Remember the local lemma said you win if d is less than 2 to the k over e, and in fact if you're careful you get 2 to the k over e here. So that proves that, as long as t is bigger than t of n, which typically is linear, okay, then with high probability, this algorithm will fail to run for t steps. Because if it did run for t steps, it would have achieved a compression of the list of those random coin flips. And so that proves that the algorithm terminates quickly. That's beautiful, right? Okay. More so if you're one of these guys like me who 20 years ago was killing ourselves trying to figure out how to prove this thing works. So this is Moser. This was his master's thesis. So if there's some early grad students here and you're not sure yet what a master's thesis looks like, this is an example. So one thing to point out, the algorithm itself in Moser's analysis proves that there's a satisfying assignment. If I know the algorithm and I know that proof and I'd never heard of the local lemma, I still know there's a satisfying assignment. Now, of course, it's very, very similar because at each step, the random reassignment is exactly what we did at the beginning of the local lemma, right? Flip a few coins instead of all coins. But it's basically the same assignment we did in the application of the local lemma. A really nice observation that I think came up for the first time in 2 different settings in these 2 papers is that, we can tinker with this algorithm and do much more interesting things in that reassignment step. Okay? And that will give us not only a nice algorithm, it'll give us new existence proofs. And for example, you know, if there's something bad with my coloring, maybe I can fix it by randomly reassigning colors to certain vertices. And it doesn't have to be uniform colors from all possible colors. It could be, for example, colors that don't appear in the neighborhood yet. And that's something we couldn't do with the straight up version of local lemma. So here's a coloring example. This is the one that to me first showed me there was some power here. Because this is a lemma that Bruce Reed and I had a lot of trouble with about 10 years ago. In fact, I spoke about this at an event celebrating the 40th anniversary of this department. So we want to color a graph, and the rule is that I don't want a color to appear too many times in a neighborhood. So here's a vertex. It's got degree delta, where delta's big, and I color it somehow. We know I can delta plus 1 color it by Brooks' theorem, but you know, conceivably I've got the color red everywhere here. So we want to put a limit on how many times red appears. And it turns out that this ln delta over ln, that's the asymptotic, so the best we can do. There's counterexamples if you know, number of 10 isn't optimal, but there's counterexamples below that. The paper actually proved that we can delta plus 1 color it. So this happens if you change the 10 to something bigger, maybe 100 or something. But the way the paper went, we had a couple steps where we used what were, you know, techniques we'd used many times before that bought us some breathing room, so that it came down to essentially something of this spirit. If you're given more than delta colors, so let's say 2 delta, can you color it so that you don't get any color appearing too many times?
Hey, Mike.
Yeah?
What's the meaning of we can?
Is it possible? Does there exist a coloring? Yes. Now, it turned out that, you know, I said back then we had some weak progress towards local lemma algorithms. The weak progress was enough that we were able to get an algorithm here, but Moser's algorithm is going to work really well on this, as we'll see. Okay? But our main concern really was the existence. Okay? So we got to there, and this gave us a lot of trouble. Like we ended up applying the local lemma, but we had to do some, I don't know, it was very painful. And then when Dimitris Akliopoulos, one of the authors on the other page, was telling me about this stuff, I realized I bet that might help here, and sure enough it does. There's a very, very simple proof. I wish I'd known this stuff 10 years ago. I'll use the same algorithm for KSAT. While there's something wrong, a bad event, well, what's the bad event? The bad event would be that there's L different vertices in one neighborhood that are all colored the same color. Let's say they're all colored red. Okay. While something goes wrong, I will reflip those. Okay. So I'll start with any coloring I want, any delta, 2 delta coloring I want. And while there is something wrong, I'll just recolor those 4 vertices. How do I recolor them? I recolor them at random, taking a random uniform color that does not yet appear in the neighborhoods. That's that thing that I couldn't do with the, you know, traditional version of the local lemma. Okay? And note that because I got 2 delta colors, I'm always going to have at least delta to choose from. So this step is meaningful. Okay? And then the exact same analysis works fairly well. Okay? So I'm going to write a history file. Okay? With KSAT, I recorded which clause I fixed. Instead of the clause, I'll record which L vertices I fixed. And I got to record a little bit more, because with KSAT, when I recorded the clause, that told you exactly what was wrong with those variables. They were all set a certain way to make that clause false. Okay? Here, if I tell you I fixed these 4 vertices, you know they all had the same color, but you don't know what that color was. So if I want to recreate the coloring backwards, step by step, I've got to also tell you what specifically was bad about them. I'll just write the color red. That means they all had the color red. Okay? And that information, so suppose I've gone T steps, I write this down to every step, I give you the coloring I'm at, Same method allows me to work backwards and reconstruct every coin flip that was made. And do I get a compression? Well, yeah, once again I do. So I've got to somehow name these vertices. I could just name all different vertices, but that takes up way too much space, especially if the labels can be enormous. So instead I point to a previous vertex. Okay? I say, you know, I had to fix these vertices up because they got messed up when I was fixing up the neighborhood of this other vertex. Okay? So this other vertex is someone that's maybe distance 2 from this. So, you know, I was fixing up V, and I look at the 24th distance, 23rd distance 2 neighbor from V. That tells me the neighborhood I'm looking in. Okay? And that's just some number between 1 and delta squared. That's bounded. And then I provide a number, you know, between 1 and delta choose L to tell me which subset of L vertices was bad here. And that allows me to specify exactly what vertices got recolored. Okay? And because each vertex always had at least delta available colors, what do I got to beat? What's the random thing I got to beat? Well, in each step, I used at least log delta random bits to pick a number from at least 1 to delta, maybe more if it had more than delta available colors. Okay? And if you just work all this out, you see this beats this, and you win. Very, very, very short proof of something that gave me a lot of pain a while ago. It's a good exercise if you want to try to work it out. If you carry out the exercise, you'll actually find out it doesn't work. There's too many delta terms here. So you're going to have to think about a slightly more concise way to say this, to save a delta term somehow. Okay? All right. So there's another example about how this technique works. Any questions up to this point? No? All right. So this is the main thing I want to talk about today, is this one. So this is an old theorem by Johansson, bounding the chromatic number of a triangle-free graph. So, you know, of course, there's always been a lot of interest in how the girth of a graph affects its chromatic number, right? So remember, you all know Michalski showed that there are triangle-free graphs with arbitrarily high girth. And then Blanche Descartes said there's graphs with arbitrarily high chromatic number. Said there's graphs with girth 6 that have arbitrarily high chromatic number. And then finally Erdős said that there's graphs with arbitrarily high girth and arbitrarily high chromatic number. So in some sense, being able triangle-free doesn't bound the chromatic number at all. But then if you think in terms of Brooks' theorem says every graph is at most delta plus 1. And if you're triangle-free, then if you have high girth, then you can do better than that. Okay? So Kim actually, a few years before this, showed that if you got girth at least 5, then your chromatic number is order delta over log delta. And then a year or two later, Johansson extended that proof to triangle-free. How did it go? Well, these are in the days that I described earlier, where when we did this, we had to give every vertex an independent color. And of course, if you give them independent colors, odds are you're going to get a lot of conflicts. A lot of neighbors will pick the same color. Okay? So many rounds of this sort of general technique that was used many times, where you randomly color every vertex, and the ones that conflict, you just uncolor them. And you hope you made a little bit of progress, and you prove that you did. And then you go again, and you go again, and you go again. You keep track of a lot of parameters. You show that each step you continue to make progress, and eventually you win. Okay? And each round you apply the local lemma again and again and again. And again, all the work is because we had to color the vertices independently, or Johansson had to. And that means that you can't keep a lot of neighbors from conflicting with each other, so you have to do some uncoloring. Okay? So now I'm going to use this new technique where we can actually repeatedly color a vertex each time with a color that doesn't appear in its neighborhood, and save all that uncoloring business and get a simpler proof. And the constant improves a bit as well. So the constant's still not tight. The lower bound comes from random regular graphs. So if you know a little bit about random regular graphs, you'll know that they have very high girth. The shortest cycle is like log n or something like that. Okay, so they got girth quite high. And the chromatic number of a random regular graph is a half delta over ln delta. That was by Acleopolis and Moore. So the best lower bound we have comes from this, so this constant might be off by a factor of 2. Okay. Although there are a couple reasons that I did like that constant. I liked getting down to 1. One of the reasons is this. I said earlier that Kim was able to prove that girth 5 has the same asymptotics. And the constant he got for girth 5 was 1 plus a little of 1. And the same constant for girth 6, for girth 7, for girth 8, for girth 1,000. Okay, you keep getting that 1 plus a little of 1. The other reason is, if you know a bit about random regular graphs, there's something called a shattering threshold. This is this business where physicists have studied random KSAT and coloring random graphs, and they tell us all kinds of stuff. You guys just hired Will Perkins, so I know you're interested in this. What happens if you look at the set of colorings of the graph? That set changes dramatically right when the number of colors is this. If you've got slightly more than this colors, then one thing is that there's simple algorithms that will produce the coloring. Okay? A major open problem in random graph theory is come up with an efficient algorithm to produce a coloring using 1 minus epsilon, delta over ln delta colors, even though we know they exist down to 1/2. We have no idea how to construct it, and this physics structure gives us some hints as to why it's hard. Another thing is this. When you want to prove that the coloring exists, the physics analysis says that when you've got this many colors, the proof examined just looks at the neighborhood, short distance, 10, distance 100, distance 1,000, constant distance neighborhood of a vertex, which in a random regular graph is just a delta regular tree. So it's just a nice local calculation based on the fact that the neighborhood of each vertex looks like a tree for a long way. Okay? When you want to get below 1 down to 1/2, you got to look at the much, much more complicated global considerations where you don't just look at the local properties of the coloring. Somehow you got to look at the colorings on random graphs align in a very nice way in a global sense. Okay? And so what this says then is that up to the point where their analysis just looked at local properties and the fact that it's a tree to a long distance, you don't actually need it to be a tree for a long distance. All you need is that there's no triangles. So up to the case where the physics analysis is local, all you really need is triangle free. Okay? And so the question, is this tight or is this the right answer somewhere in between? If the right answer is a bit lower, it would mean that every triangle-free graph, the colorings line up in that global way, which seems trickier to get a handle on. Anyways, that's just some talk about the constant 1. Let's get on to the proof. So the proof is going to be, like I said on the previous problem, I'll repeatedly color vertices using colors that are not in the neighborhood. Now remember with the other coloring problem, we had 2 delta colors. So there's a guarantee that there's always some color not in its neighborhood. In fact, a lot of colors. But this is the challenge in this problem. I got no guarantee there'll be a lot of colors. In fact, there might not be any. I've got far fewer than delta colors to start with. So what I'm going to do is this. My bad event is going to be that V doesn't have very many available colors. So I'm going to try to set things up so that everyone has a lot of available colors. It seems a bit circular. It's going to take a while for this to hone in on something that actually works. Okay? But the idea is this. I want to basically, as I modify my coloring, ensure that everyone has a lot of available colors. So what do I mean by a lot? What should I aim for? Well, let's suppose I've got 1 plus epsilon. So epsilon can be any constant. That's, if I prove this for any constant, I get the 1 plus a little of 1. So I've got this many colors. Let epsilon be any small constant. Take this many colors. And, remember, I'm going through my graph. I'm coloring it at random. And at some typical stage, I look at a vertex and I wonder how many colors are available for it. Okay? And the point is that all of his neighbors have been colored randomly somehow, in a complicated way. But to start things off, to give me something to aim for, I thought about, well, let's suppose it was an uncomplicated way. Let's suppose that each neighbor was just assigned a uniform random color. That's not really what happened, of course, right? But let's pretend to give me something to aim for. So I assign each vertex a uniform random color. Note that I can think of them as being independent because there's no edges down here. That's why where triangle free helps. Okay? So assign each vertex a uniform random color and ask how many colors are not assigned at all. That's a standard problem. It's called the coupon collector's problem, well analyzed. Okay? And a very simple exercise is that I expect roughly delta of the epsilon colors available at the root. Okay? This is where the proof breaks down if I try to go below 1. If I have 1 minus epsilon, then I don't expect any colors available. So this is why 1 is the limit. So I expect something like delta to the epsilon, and so I'll set a target, a lower bound. I want everyone to have delta to the epsilon over 2, so quite a bit less than this. Okay? This will be my goal. So here's my first attempt at an algorithm, which really doesn't make sense, but bear with me. While there's a vertex with fewer than L, delta to the epsilon over 2, colors available, then I'll fix it by recoloring its neighborhood. And when I recolor its neighborhood, I give everyone a random color from their own list. Okay? But this feels circular, right? Like, I mean, what if these lists are all small? Okay? These lists could all be bad, and this line doesn't work very well. For example, if these lists each have size 1, then recoloring at random doesn't change anything. And then there's a bigger problem. How did I start this off? I mean, implicitly, I've got this coloring that I'm tinkering with, and the whole point is to find a coloring. Okay? So to solve both those issues, what we're going to do is I'm going to allow us to leave some of the vertices blank. Okay? So, and that helped with this recoloring. So there's a number of ways you can implement this idea. At first I tried saying, if U is a good vertex, if it's got a lot of available colors, then I just pick a color. And if U has fewer than L available colors, then I can leave it U blank or something like that. And there's a bunch of versions. And the one I settled on that ended up working best is I'm simply going to add the color blank to every list. So when I pick a color at random, there's one extra color thrown in there. It's called blank. And if I pull that one out of the bag, it means I've left the vertex blank. And so indeed, every vertex can be blank, even the ones with big lists. But of course, the ones with big lists are unlikely to become blank. The ones with tiny lists have a pretty good chance of becoming blank. Okay? And that's enough to make this recoloring step useful. Okay? Note that if it's got a really small list, which should be a problem for me, it's got a high chance of getting blank. And blank helps me because I want to have a lot of available colors up here. So every time I pick blank for one of these vertices, that just helps me have a lot of colors up here, right? So that's a good thing. And it also helps the issue of how do I start the algorithm? I'll just start with every vertex blank. Okay? But of course, this introduces some other potential problems. What if I want a coloring? I don't want half the graph to be blank. And in fact, if I start with every vertex blank, I won't go anywhere because every vertex is good. Every vertex has lots of available colors. Okay? So this doesn't work so well. So I'm going to have to introduce a second bad event. I don't want too many blank vertices around my graph. So my second bad event will be that some vertex has too many blanks. And what am I going to use for too many? I'm going to pick L. And why did I pick L again for the too many? Because that means that there's no bad events. I can finish it off greatly. Right? If I ever get to a point where there's no bad events, that means every vertex has a list of size at least L. And every vertex has fewer than L blank neighbors. So the greedy algorithm wins. Okay? So those are my two bad events. Okay? So now here's my revised algorithm. Start with L blank coloring. While there's a vertex with either bad event going on, I recolor its neighborhood. Okay? And an important point is I'm going to prioritize this event. I'm not going to touch any of these until this is cleared up everywhere. Okay? And why is that good? Because if this is cleared up everywhere, it means everyone's got a big list. And so when I try to address this, it's unlikely that I'll get a lot of blanks in a neighborhood because everyone's got a big list, so everyone's unlikely to get blank. Okay? So this bad event is unlikely to hold. Okay? What about this one? I said earlier it's unlikely, but that was on that really simple coloring process. Right? Earlier on I said if everyone got just a uniform color, then I expect a lot of colors available at the root. But that's not what's happening. Okay? In fact, the way this worked was when I came to color this vertex at some step in the past, I gave it a random color from all the available colors, which was basically colors that didn't appear on its neighborhood at that time. And then so it got colored from a list. And this vertex got colored from a different list, maybe a really small list, maybe red and blank. Maybe the list only had the color blank in it. Okay? But each one of these, I didn't give each vertex an independent color from 1 to q. I gave them independent color from some list that, as far as I know, an adversary came up with. Okay? So really what's happening is the adversary gives every neighbor a list, which includes blank, and I still get to treat the assignments as independent, at least for the analysis that I end up needing, that suffices, okay? Because there's no edges between them. Okay? And now here's the really nice thing. Here is the miracle that allows this entire proof to work, is that the adversary doesn't get any more power by choosing these lists. Giving everyone the same list 1 to q is the worst set of lists. Well, it's not quite the worst, but it's close enough to the worst. No matter what lists the adversary gives, I still get roughly the same expected value at the root. Okay, the same expected number of available colors. Okay? Again, no matter what the adversary does outside of this, I still get what I want to happen at the root, just as if I'd given them all a random color. When I try to apply this technique to other problems, which I have and been very frustrated by not being able to do it, it's usually this is the point where it breaks down. That things look really nice if I were to assign colors randomly, but if I let an adversary set things up outside, he can mess things up badly. But this time he couldn't. Okay? So this time, no matter what the adversary does out there, I expect a lot of colors to be available. And of course, expectation's not enough. You've got to prove concentration. You've got to prove that with high probability the number of colors is going to be close to the expectation. So basically this says that, that E shouldn't be there, but it's not really that harmful. It says that the probability I fail, the probability that I have too few colors at the root is small, like delta to the negative 10 or something. So again, here's my algorithm, beginning with all blank. Wall is a vertex with not many colors available. Fix it. If all those are fixed and there's a vertex with too many blanks, fix that. That might create this problem somewhere else, so I fix it and I keep going. Okay? Okay. So I've already said on the previous slide that the probability that this goes wrong is small. If the lists are all big, then it's easy to compute that the probability this one goes wrong is small. Okay? If you actually carry out the computation, you find, wait a minute, that doesn't work. It only works when I've got at least 2 times the delta over log delta colors. Okay? To get down to 1, I have to use a more complicated second condition. Basically one that doesn't just count the size of the list compared to the blanks, it takes into consideration what lists appear in the blanks. That second condition was a common one that we used in this sort of thing. I didn't require any creativity to come up with it. And I'll be a bit repetitive here. Okay. I want to show that if this algorithm goes for too long, then I've got a compression. Okay. So I get a contradiction. It couldn't really go on for too long. Okay. So I claim that as I run the algorithm, I can record something that will allow me to recreate every random choice that I made. Okay. At each step, I write down what vertex did I fix, and what was wrong with its neighborhood. Okay? On the first example, I didn't have to write anything about what was wrong. I just named the bad clause. And if I tell you the clause is bad, you know what's wrong. All the variables were set the wrong way. On the second problem, I told you the bad set of vertices. All that you know is what's wrong is they all have the same color, so I had to tell you the color too. Okay? This time, I'm going to have to tell you, what all the colors were that made it bad. And from this list of colors, you can see, oh yeah, there weren't very many available for it. Or, oh yeah, there's way too many blanks. Okay? So I'm going to have to come up with some way to write this and this efficiently. Okay? So I write down the name of the vertex that got fixed. I write down the bad coloring that was on its neighborhood. This record allows me to reconstruct everything. just like before, I work my way backwards. I've got a coloring. I've gone on for t steps for some big value of t. I've currently got this coloring, partial coloring. It's got some blanks, some others. I know that the last step was to fix this vertex by recoloring its neighborhood. And the reason I had to do it was because this neighborhood had those colors. So that tells me what the previous coloring was. And I keep working backwards. Okay? So this information allows me to reconstruct all the random flips. Okay? And the second claim is that as long as t is big, we've gone many steps, that this record is smaller than if I just recorded all the colors. Okay? And how can I make it small? Well, there's two things. I've got to write down the name of the vertex that I fixed. That doesn't take much space because of those degree bounds again. Instead of naming the actual vertex, because it might have an enormous label, I point to an earlier vertex that when I addressed that neighborhood, I messed this vertex up. And I say it was the jth second neighbor of that earlier vertex, where j is a small number. It's at most delta squared. And then I got to name this bad coloring. And the reason it doesn't take much space is because bad colorings are rare. If I take a uniform random coloring of the neighborhood, the probability that it's bad is small. And that means the number of bad colorings is small relative to the number of actual colorings. Okay? And so I just write down it's the nth possible bad coloring of the neighborhood for some fairly small L. Okay? And again, why is L small? Because there's not very many bad colorings. The probability of coloring is bad is small. And to win, well, if I wanted to actually record, just repeat all the random colors, instead of writing down the name of the vertex and the bad coloring, I'd simply write down the new coloring every time. That would give me my list of all the random colors. I want to show this is smaller than this. Okay. Well, how big is this? Well, we added the logs, so it's multiplying the actual number. The size of this is what the degree bound tells me I need to write down the name of the vertex, and how many bad colorings there are, times an order 1 to take track of the tree business and so on. Okay? So that's how much work it takes to take this, write this. How much work does it take to write down the new coloring? Well, I took a uniformly random coloring of the neighborhood. So it's just how many colorings are there? So I want this side to be smaller than that side. I rearrange a little bit, number of bad colorings divided by the number of colorings. This simply says the degree bound times the probability of bad is order 1. That looks an awful lot like the local Lemma condition, right? But there's a key difference between this and the local Lemma condition. Okay? Here the degree bound just tells me how many of these neighborhoods intersect each other. Okay? When I fix this neighborhood, how many other neighborhoods could I mess up because we share a vertex? So the degree bound is strictly intersecting. Okay? In the local lemma, the degree bound talked about dependency. How many neighborhoods down here are somehow dependent on the random choices we made here? The dependency spreads all over the graph. So I win a lot by it being able to interpret degree bound as number of events that intersect, not number of events that are dependent. Okay. That's all I'll say about the triangle-free graphs. Any questions? Okay, good. So Johansen also proved something about KR-free graphs. Let's say K4-free graphs, K10-free graphs. For each constant R, he gets almost the same bound. R is a constant, so ignore that. This is a constant that just is linear in R. There's a conjecture that's been around for many years that says we should be able to get order delta over log delta. And Johansen got an extra log delta term. Okay. And again, the tricky part is that it's not triangle free. We've got lots of edges down here. We know the clique number of the neighborhood is bounded, but there's a lot of edges, so it's not as easy to recolor. They're not independent anymore. So this approach works as well here. In my paper, I end up with the exact same constant, which is something of a coincidence, although, we weren't actually, when you see a number like 200, you know he wasn't aiming for the best one. And we think that the whole asymptotic order is wrong, so there's no point really trying to improve the constant. Okay? Unless we're wrong about it, and that is the right asymptotic order, but we don't think we are. So, same thing, begin with all blanks. While there's a vertex with not enough colors available, or too many blank neighbors, we recolor its neighborhood. But this is where things get a bit more tricky, right? When there is no edges, I just flip a coin on each vertex, or pick a random color on each vertex, independently. Because there's so many edges, I can't do that. The color I pick for this vertex affects the colors that I give these two. So what I have to do is I take a random partial list coloring. So again, remember the adversary has given me lists on every vertex. Okay? And I look at those lists, and I look at the subgraph induced by the neighborhood, and I write down every possible partial coloring of that subgraph. Partial meaning I'm allowed to put blank in some spots. And I throw all those colorings in a bag, and I pull one out uniformly at random. Okay? And then I do the same analysis. Okay? Now, that seems like a nastier thing to analyze, right, than do some independent flips. Thankfully, I was able to think of a way to analyze it. And perhaps I'll say a little bit about it in a few minutes. One thing I'll note is that Shearer, shortly before Johansen, proved that the largest independent set is what basically this tells you. Okay, so if you've got a coloring with this many colors and divide n by the number of colors, then this is the size of the independent set. So this is the bound that you need to have a chance at this. Okay? We think the log delta can be eliminated here. So it makes sense to aim for this problem before you try to aim for this one. Okay? I'm saying this partly just to tell you, a relevant result, but also this had a lot to do with this and also with my work here, because what Shearer also actually looks at is the average independent set. Okay, so he says if you pick an independent set, average independent set from the graph, then this is the expected size. So again, throw every independent set into a bag, pull one out, and count that size. Again, that seems like a nasty thing to analyze, but he came up with a clever way of analyzing it. Okay? And a random partial list coloring is, in a sense, a collection of independent sets. Right? So in spirit, something like this might work here, and in fact it did. And I guess that's all I'll say about it. Okay. I think that's my last slide. All done. Thank you.
I have two questions. The first one, in the girth problems, you had a bound of 1,000. I presume 1,000 was just a generic 1,000,
generic,
not a particular
yes.
1,000.
Yes. Yeah.
The second question, the Lovász local lemma that you stated at the very beginning had a very nice, clean, simple form in some sense. Is there something like that for the new technique?
Yes. So first I'll say that was a nice simple form. There's many, less and less and less simple forms that have more and more and more power. Okay? So for this new technique, Akleopoulos and Iliopoulos came up with, give one expression that's very, very similar flavor to that. I won't write it down, but it's because I'll probably forget it. You'll watch me fumble around trying to get it right. But it's very similar looking. It doesn't give the full power. In particular, I couldn't make either of the two coloring results I gave fit into that formulation. So, but there is a formulation that will work often.
Are there any further questions?
Can you recommend a tutorial Can you recommend a tutorial besides your talk, helping us to understand Moser and Johnson and related stuff. In particular, are you updating your older book?
I'm not updating the older book.
You should.
Thought about it briefly a few years
What?
ago, but I thought about updating it a few years ago, but then we quickly bailed out. The best spot to see that presentation of Moser's proof is on Terry Tao's blog. You know, the version that Moser wrote in the paper wasn't quite as crisp as this. The story goes that after he wrote his paper, he was preparing a talk at Stock, and while he was preparing his slides, he realized, oh, there's a much nicer way to present this. So, and then that just sort of kind of spread. But I would look it up in Terry Tao's blog. As far as this whole general technique, I don't know of a very clean tutorial. I don't know of anything written with the purpose of the goal of teaching the technique yet. It's still fairly new. But there's scattered papers, and maybe reading a few of them will get the picture across.
Could you simply write a volume 2 without
Pardon me, could I simply write?
Could you simply do a volume 2 to adjoin you?
I could do a volume 2. I don't know if I could simply do it.